the June 2015 Regents exam in chemistry. This is a walkthrough of part B-1. This part of the exam consists of 20 multiple choice questions from throughout the curriculum. To skip to a particular question or to view the answer key for this part of the exam, click on the index button that appears in the upper right corner of the screen. Here is question number 31. Which electron shell contains the valence electrons of a radium atom in the ground state? To help with this question, we bring in a small segment of the periodic table and notice that radium is located in the 7th period of the periodic table, which indicates that it has 7 electron energy levels. The first two have been omitted for the sake of saving space on the periodic table, so there should be a 2 and an 8 prior to this number 18. Then we have 32, 18, 8, and 2. So there are 7 energy levels. The outermost one, or 7th in this case, is the valence shell. So radium has its valence electrons located in the 7th shell. Answer number 3. Question 32. Each diagram below represents the nucleus of an atom. So they're showing us 4 atoms here. How many different elements are represented by the diagrams? There are 4 different atoms. However, the first 2 atoms have 1 proton each. And since the number of protons designates what type of atom you're dealing with, these are both atoms of the same element. The second pair of models have 2 protons each, so they are both atoms of the same element as well. So there are 2 different kinds of elements pictured here. It's answer number 2. Number 33. Chlorine and element X have similar chemical properties. An atom of element X could have an electron configuration of, and they give us 4 possible electron configurations for our element X. Let's take a closer look at chlorine. Chlorine has an electron configuration of 2-8-7, so it has 7 valence electrons. If you recall, what makes properties of elements similar to other elements is the arrangement of their valence electrons. So since chlorine has 7 valence electrons, we would expect element X, being similar in properties, should also have 7 valence electrons. So we go back and look at our 4 available electron configurations and note that only answer 4 has an electron configuration with 7 valence electrons. So that will be the element that has properties most similar to chlorine. Our answer is 4. Question 34. Which group of elements contains a metalloid? And we're given 4 choices, group 2, 8, 16, and 18. Well, let's take a look at a graphic that shows the locations of the metals, the nonmetals, and the metalloids. We're looking for a metalloid. Group 2 is entirely made up of metals, so that's out. Group 8, all metals. Group 16 has some nonmetals. It also has, right there, a metalloid, and then it also has some metals in it. And group 18 is made up almost entirely of nonmetals, and there's one element that borders on being a metal, perhaps. But the only group that has a metalloid in it is group 16. So we go back to our question, and we select answer number 3. It's group number 16. Question 35. Which Lewis electron dot diagram represents a fluoride ion? Well, since we're looking for an ion, we can immediately eliminate answers 3 and 4 because these are not ions. They don't have any charge represented. Now, that leaves us with choices 1 and 2. So let's investigate a little further what a fluoride ion is. From the periodic table, we notice that the favored oxidation state of fluorine is -1. And to have an electron arrangement where you have a charge of -1 means you must have gained 1 electron. So typically, if fluorine has 7 electrons in its valence shell, if it gains 1, it now has 8. So we're looking for a diagram that has 8 valence electrons represented. Back to the responses. The first picture shows a fluorine nucleus with 8 valence electrons and an overall charge of -1. That's going to be our answer. It's answer number 1. What's wrong with number 2? It only shows 7 electrons, the original valence electrons, we assume. So since it doesn't show the extra electron, it's not a valid representation of a fluoride ion. Answer 1. Question number 36. In the formula for the compound XCl4, the X could represent any one of these 4 atoms, carbon, hydrogen, magnesium, or zinc. Well, let's recall how we wind up with a chemical formula of XCl4. From our formula writing experience, we know that if we look at the oxidation states of the two elements in the compound, and if we were to take those oxidation states, the chlorine being a -1, as you can see from the periodic table, chlorine's negative oxidation state is -1, and that number has been crisscrossed and used as a subscript after the element X. So whatever the X has as its oxidation state has been crisscrossed to the chlorine. And we can see that number was a 4. So we expect our element X to have an oxidation state of +4. Now if we review the 4 possible answers here, the carbon, hydrogen, magnesium, and zinc, the only one that's listed as being capable of a +4 oxidation state is the carbon. Magnesium is a +2, as is zinc, and hydrogen can only be ±1. So our answer is going to center around carbon, because it's the only one that can be +4. So the answer is 1. Question 37. The formula C2H4 can be classified as, and there's several different descriptions here of what kind of formula that is. Well, when we write a formula using symbols and subscripts, those are molecular formulas, or if they're an ionic compound, they would just be a chemical formula. Certainly this is not a structural formula. So we're going to eliminate both answers that say structural formula. A structural formula would have this appearance. We would have our 2 carbons, in this case that'd actually be a double bond, and you would see all of the atoms represented and showing connections using dashes for the bonds. So it's not a structural formula. So it's a molecular formula. But is it also an empirical formula? Well, if you recall, an empirical formula is the simplest whole number ratio of elements displayed in the formula. This formula is C2H4. We could simplify the C2H4 into a simpler form, in which case it would be CH2. But writing it as C2H4 then is a molecular formula. It's not in simplest form, so it is not also an empirical formula. So we're going to stick with answer number 2. This is a molecular formula only. Question 38. Given the balanced equation representing a reaction, here's your equation, how many moles of aluminum react completely with 4.5 moles of the oxygen to produce 3 moles of the aluminum oxide on the other side? There's a couple of ways to go about this, but this is a typical stoichiometry problem utilizing moles. So let's take a look at our 3 characters, the aluminum, the oxygen, and the aluminum oxide. The ratio of moles from the equation is 4 to 3 to 2. These are the coefficients that appear before these formulas in the equation. And we know that at the end, we're going to have 4.5 moles of oxygen being consumed, and we're going to produce 3 moles of the aluminum oxide. So whatever number goes with the aluminum has to be proportional in a 4 to 3 to 2 proportion with the numbers 4.50 and 3. This pair of numbers seems to be the easiest one to work with. So 2 is to 3 as 4 is to 6. So our answer is going to be 6 moles of the aluminum reactant in order to completely use 4.5 moles of oxygen and produce 3 moles of aluminum oxide. So this answer is 3. Question 39. What is the percent composition by mass of oxygen in calcium nitrate? They've given us the gram formula, mass of 164. We're looking at the oxygen component, and we notice that there are 2 times 3 or 6 oxygen atoms in here. And hopefully you recall, or you could look it up on the periodic table, but an oxygen atom has a mass of 16. So the total mass of our part, our oxygen part, is going to be 6 times 16. Now, to compute the composition by mass, the formula for that on table T is mass of the part divided by mass of the whole thing times 100. So here's our mass of the part, 6 times 16 for the oxygen, which is 96. And the 164 is the formula mass of the whole compound, 164. So 96 divided by 164 times 100. And that's going to result in a computation that comes out to 58.5%. So we'll select our answer, that is 58.5%, and the rounded off version of that is answer 4, 59%. Question 40. Given the balanced equation representing a reaction, there you go, which type of chemical reaction is represented by this equation? Don't let the little number 6 intimidate you. It looks like it's very complicated with all these numbers in it, but ultimately you're looking at a very simple answer here.
You must recall that there are four basic reaction types. A synthesis, in which you take two simple things, let's call them A and B. They go together to form a compound. Decomposition, where you start with the compound and you can break it apart into pieces. Single replacement, where you have a single element added to a compound, and the single element replaces one of these two elements to produce a new compound. In this case, we'll go with A, C, and B. And then double replacement, where you have two compounds, and they literally switch partners, and you wind up with an AD and a CB in this case. So which pattern do we see taking place in our reaction? Well, lithium's an element by itself, nitrogen's an element by itself, and you're putting them together to form a compound. Clearly a synthesis reaction, answer 1. Question 41. Which elements can react to produce a molecular compound? That means that they're going to react and produce a covalent bond. We could take the time, look up all the electronegativity values here and compare their differences. We'd be looking for the pair of elements that has the lowest difference in electronegativity. But rather than doing that way mathematically, let's take a look at their position on the periodic table. Hydrogen is kind of unique among the metals. It has, compared to the other metals, it has a fairly high electronegativity. It doesn't really want to give up its electrons as vigorously as these other ones do. So the metal strength is important. These three metals are all pretty strong metals. The hydrogen's considered the weak metal. On the nonmetal side, fluorine we know is the strongest nonmetal. Oxygen takes a pretty close second place. Chlorine would be third in this pile. And sulfur would be the weakest of the nonmetals. So to get a low difference in electronegativity, we're going to take the weakest metal, hydrogen, and the weakest nonmetal, sulfur, and this would be the pair most likely to form a covalent bond. So it's the hydrogen and sulfur, answer 2. Question 42. Compared to a 1 mole sample of sodium chloride in the solid state, a 1 mole sample of sodium chloride in the liquid state has a different, well, the only thing different about them is that one's a solid, one's a liquid. So let's take a look through the answers and see which one of these could possibly be different. Number of ions? Well, no, they're both 1 mole, so they're exactly the same number of ions. That answers out. Empirical formula. Well, these are both empirical formulas, NaCl, and it's the same empirical formula, so that answers out. Gram formula mass. The formula mass of NaCl is the same as the formula mass of NaCl, so that answers out. So by process of elimination, our answer is 4, but let's see if it makes sense. To conduct electricity, an ionic compound such as sodium chloride has to be in the liquid state so that the ions are free to move around. In the solid state, the ions are not free to move around. So sodium chloride does not conduct electricity in the solid state, but it does conduct electricity in the liquid state, making electrical conductivity the one property of those listed that is different. Answer 4. Number 43. Which property of an unsaturated solution of sodium chloride in water remains the same when more water is added to the solution? Well, let's take a look at what our solution might actually look like. We have a container with water, and there's sodium chloride dissolved in it, here represented by the little green and red dots. Those are the ions of sodium and chlorine. Now, if we come along and we add more water, we raise the line here where the water is, eliminate that line, the sodium and the chloride ions are going to have more space in which they can move around, but we're not changing the total number of them. So let's take a look at what things we're actually changing here. Would the density of the solution change in that situation? Yeah, I believe it would, because we're spreading out the mass over a greater space. So it's not going to be that one. Boiling point of the solution, would that change? Yes, it would, because you're changing the concentration of the solution, therefore you're going to also affect the boiling point. That's a colligative property of the solution. Are we changing the mass of the sodium chloride in the solution? Well, no, we added water. We did not add more sodium chloride, and we didn't take any out. So that's the one that does not change. It's number 3. So the answer is going to be 3. The mass of sodium chloride stays the same. And to be thorough, does the percent by mass of water in the solution change? Yes, because we added more water without altering the amount of sodium chloride. So only number 3 works, and we're going to stick with that as our answer. Question 44. Which ion combines with the barium 2 plus ion to form a compound that is most soluble in water? And we're given our choices of the sulfide, the hydroxide, the carbonate, and the sulfate ions. So this is a question that's going to center around Table F, the solubility guidelines for aqueous solutions. I've highlighted the 4 possibilities here: carbonate, sulfide, hydroxide, and sulfate. So let's start over here with the sulfate. Sulfates usually dissolve in water quite well. There is an exception, however, where barium is involved. In other words, barium sulfate would not be very soluble. Let's take a look at the carbonate. Normally, carbonates are not very soluble unless you put them with group 1 elements or ammonium ions, which barium is neither of those. So again, the carbonate one's not going to be the answer because we're not going to have very good solubility with barium. Sulfide, same as the carbonate. It doesn't dissolve very well unless you put it with group 1 or ammonium, neither of which describes barium. So that guy's out also. That's going to be insoluble. And finally, our answer, the hydroxide. Hydroxides don't dissolve very well unless you combine them with certain ions, including the barium plus 2 ions. So the barium hydroxide will be the most soluble from among those answers provided here. So we're going to go with answer number 2, the hydroxide. Number 45. When a sample of gas is cooled in a sealed, rigid container, the pressure that the gas exerts on the walls of the container will decrease because the gas particles hit the walls of the container. We have to decide whether they're hitting less often or more often, and with less force or more force. Those are our things that we're working with here. What are we doing? We are cooling the gas. That means we're slowing the particles down. Well, if they're moving more slowly, they're not going to hit the walls as often. So we're going to stick with less often. And if they're moving more slowly, they'll hit the walls with a little bit less force as well. So our answer is number 1. Cooling off the gas is going to make the particles collide less often and with less force. The result will be the lower pressure that is observed. Answer number 1. Question 46. A rigid cylinder with a movable piston contains 50 liters of a gas at 30 degrees Celsius with a pressure of 1 atmosphere. What is the volume of the gas in the cylinder at STP? So they didn't give us the finishing temperature and pressure, but they did tell us it's STP. So in other words, we know what the temperature and pressure will be at the end because we know what STP stands for, your standard temperature and pressure conditions. So we have 4 numerical answers. We're going to have to do a calculation, and this calculation is the combined gas law calculation. So from table T, we can bring in our gas law. And I've listed in the purple writing here all of the different variables that were provided to us in the question. We were told that the initial gas had a volume of 50 liters, temperature of 30 degrees Celsius, with a pressure of 1 atmosphere. I'm going to change the temperature right away, which you have to do. You can't do a gas law problem in Celsius temperature scale because we can't introduce any negative numbers here. That would really cause a great deal of problem. So we have to use kelvins. The STP, we know that standard pressure is 1 atmosphere and the standard temperature is 273 K. So I have my P2 and my T2. We're looking for volume 2. Notice that the pressure doesn't change. P1 is the same as P2. So let's pull that completely out of our calculation. We don't have to worry about pressure in this case. So if I modify the gas law, only including the volumes and the temperatures, I get the expression V1 over T1 equals V2 over T2. Now I can plug in the numbers. So it's going to be the 50 liters divided by the initial temperature of 303 equals the final volume, V2, divided by the 273. Now you can see that these numbers aren't too far apart. So 50 over 303 is going to be equal to something a little bit less than 50 over 273. So let's take a look at our answers. You, of course, could calculate this with your calculator, but when you're done, you're going to get answer number 2, 45 liters. Answer 2, combined gas law problem. Question 47. Given the potential energy diagram for a chemical reaction, and here it is, very nice potential energy diagram, which numbered interval represents the heat of the reaction? Well, heat of the reaction is the difference between where you start the equation and where you finish. So if we look at our graph, we can see the starting point right here. And we can see the ending point right here. So the distance between those 2 points is the interval between the 2 dotted lines. That's going to be answer number 4. Questions 48 and 49 are based on the graph that's provided on the test, which show the normal boiling points for 5 different alcohols. Question 48. What is represented by the number 1 in the IUPAC name for 3 of these alcohols? These are the names of 3 of the alcohols involved. You can see they have little 1s in front of them. So what do those 1s stand for? Well, in our organic chemistry unit, we learn that alcohols, represented here by the ANOL suffix on the name, must contain a hydroxyl group somewhere on their structure. In the first structure, prop means there's 3 carbons, and the 1 tells us that there is a hydroxyl group on the first carbon. If we're counting carbons from left to right, that would be here. The second structure, the 1, tells us the OH is again on the first carbon, and even the last one, it's on the first carbon. So the purpose of the number in front of the name is to tell us the location of the hydroxyl group. So the answer that corresponds to that idea is the third one. It's the location of an OH group on one end of the carbon chain in each alcohol molecule. Answer 3. And question 49, what can be concluded from this graph? Let's analyze each of the answers because they're pretty varied. At 101.3 kilopascals, which this graph is based on, water has a higher boiling point than 1-butanol. Well, let's see if it does. What is the boiling point of water under normal conditions? It's 100 degrees Celsius. And 100 degrees Celsius is where this red line is that I just drew on the graph. So 1-butanol has a boiling point that's above that. Does water have a higher boiling point than that? No, it's actually lower. Water has a lower boiling point than ethanol. Let's see if it does. Ethanol's boiling point is below that line, so no, it's the opposite of that as well. Consider the third answer. The greater the number of carbon atoms per alcohol molecule, the lower the boiling point. Now, methanol has 1 carbon, ethanol's 2, prop for 3, bute for 4, pent for 5. If you don't remember what the prefixes mean, remember that you can always look that up on table P. So here are your alcohols, the methanol, your ethanol, the butanol, and the pentanol, and propanol, okay? That it ranges from 1 to 5 carbons. So what's happening to the boiling point on this graph? Well, as you're going from 1 carbon to 5 carbons, the boiling point goes up, not down. So it's not answer 3. The greater the number of carbon atoms per alcohol molecule, the higher the boiling point of the alcohol. That's exactly what's happening. The answer is number 4. And the final question on part B1, number 50. In the laboratory, a student investigates the effects of concentration on the reaction between hydrochloric acid and magnesium, changing only the concentration of the hydrochloric acid. Data for 2 trials in this investigation are shown in the table below. So in the first trial, the concentration of the hydrochloric acid is 0.2 molar, and in the second trial, it's 0.4 molar. So that's the variable that's being controlled here. That is what's being increased. So we are asked to speculate, compared to trial 1, what do we expect the reaction time for trial 2 to be, and what would be the explanation for the result? So hopefully you recall that if we increase the concentration of reactants, we're going to have more effective collisions at a more rapid pace. That should actually make the reaction go faster. So the amount of time it takes for the reaction to take place is going to be less than it did when you had the lower concentration. So our question mark here should be a number less than 48. Let's see which answers work. 3 and 4 are gone because they're expecting the reaction to take longer. So less than 48 seconds. And what did we say the reason was? Because there are more effective particle collisions per second due to the increased concentration. The answer is number 2. And that concludes part B1 on the June 2015 Chemistry Regents exam. Look for additional videos for parts A, B2, and C of this exam. Thanks for watching. You can access additional videos and materials for this and other chemistry exams at alchemtutor.com. For questions, comments, or permissions, please contact me at my email address at asnyder@alchemtutor.com. If you have interest in contracting tutorial services, you can also contact me through the website at alchemtutor.com.